Hello and welcome to the episode 13. Remote Sensing Fundamentals. You are watching Afeez Azeez Geospatial Academy, a learning platform where you will discover everything about the fascinating field of surveying and geoinformatics. Welcome to our new series titled Geospatial Science Explained, a brand new series. In the series, we will dive in deeper into the world of surveying and geospatial science as it relates to our daily activities. Today, we are talking about episode 13, Remote Sensing Fundamentals. Introduction. Imagine being able to monitor an entire rainforest without stepping into it. Imagine measuring the health of crops across thousands of hectares without visiting every farm. Imagine detecting oil spills, monitoring urban growth, tracking floods, predicting droughts, assessing environmental change, and observing natural disasters from hundreds of kilometers above the Earth's surface. How is this possible? How can we gather information about places we cannot physically reach? How can satellites observe our planet every day and provide critical information for decision-making? The answer lies in one of the most powerful technologies in modern geospatial science: remote sensing. Remote sensing allows us to collect information about objects, features, and phenomena without making direct physical contact. Today, remote sensing plays a central role in agriculture, forestry, environmental management, disaster response, urban planning, climate science, defense, and sustainable development. Welcome to Geospatial Science Explained. In this episode, we will explore the principles of remote sensing, electromagnetic radiation, remote sensing systems, sensors and platforms, satellite imagery, image characteristics, data acquisition processes, applications of remote sensing, emerging technologies, and the future of Earth observation. By the end of this lesson, you will understand how remote sensing enables humanity to observe, measure, and monitor our planet on an unprecedented scale. Before we continue, please remember to subscribe to this channel, like this video, share it, and drop a comment below. Your support helps us grow this academy. Chapter 1. What is remote sensing? Remote sensing is the science and technology of obtaining information about objects, areas, or phenomena without making physical contact with them. The term remote means distant. The term sensing means detecting or measuring together. Remote sensing refers to gathering information from a distance. Instead of physically touching an object, sensors detect energy reflected or emitted from it. This information is then analyzed to identify characteristics and conditions of the object being observed. Simply put, remote sensing is observing the Earth without physically being there. Chapter 2. The history of remote sensing. The origins of remote sensing can be traced to aerial photography. In the mid-19th century, photographs were captured from balloons and kites. During the First and Second World Wars, aerial photography became an important tool for military reconnaissance. The launch of satellites in the 20th century transformed remote sensing dramatically. A major milestone occurred in 1972 with the launch of the first Landsat satellite. Landsat provided systematic observation of the Earth's surface and revolutionized environmental monitoring. Today, hundreds of satellites continuously collect data about our planet. Modern remote sensing has become an essential component of geospatial science. Chapter 3. The science behind remote sensing. Remote sensing depends on one fundamental principle: energy interaction. Objects interact with electromagnetic energy in different ways. Some energy is reflected, absorbed, transmitted, scattered, emitted. Sensors detect these interactions and convert them into usable information. The characteristics of reflected and emitted energy reveal important information about Earth's features. Chapter 4. Electromagnetic radiation. The foundation of remote sensing is electromagnetic radiation. Electromagnetic radiation consists of energy waves that travel through space. Examples include radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, gamma rays. Together, these form the electromagnetic spectrum. Remote sensing primarily utilizes specific portions of this spectrum to observe Earth. Chapter 5. The electromagnetic spectrum. The electromagnetic spectrum represents the entire range of electromagnetic energy. Different remote sensing systems operate within specific wavelength ranges. Key regions include visible spectrum, near infrared, shortwave infrared, thermal infrared, microwave region. Each region provides unique information about Earth's surface. Understanding these regions is essential for interpreting remote sensing data. Chapter 6. The visible spectrum. The visible spectrum is the portion of electromagnetic energy detectable by the human eye. It includes blue light, green light, red light. These wavelengths allow us to see color. Many remote sensing systems capture visible light because it closely resembles human vision. Visible imagery is widely used for mapping and visual interpretation. Chapter 7. Infrared radiation. Infrared radiation extends beyond visible red light. Plants strongly reflect near-infrared energy. Healthy vegetation reflects more infrared energy than stressed vegetation. This property makes infrared imagery extremely useful for agriculture. Forestry. Environmental monitoring. Vegetation assessment. Infrared observations provide information that cannot be detected using visible imagery alone. Chapter 8. Thermal infrared radiation. All objects with temperature emit thermal energy. Thermal sensors detect this emitted radiation. Thermal imagery allows scientists to measure surface temperatures. Applications include wildfire monitoring, urban heat studies, volcanic activity monitoring, water temperature assessment, industrial inspections. Thermal remote sensing provides critical environmental information. Chapter 9. Microwave remote sensing. Microwave energy possesses unique properties. Unlike visible light, microwaves can penetrate clouds, haze, and even some vegetation. Microwave sensors operate day and night. Radar systems use microwave energy extensively. This capability makes microwave remote sensing extremely valuable for all weather monitoring. Before we continue, please remember to subscribe to this channel, like this video, share it, and drop a comment below. Your support helps us grow this academy. Chapter 10. Energy interaction with the Earth. When electromagnetic energy reaches the Earth's surface, several processes occur. Energy may be reflected, absorbed, transmitted, scattered. The proportion of each process varies depending on the object being observed. Different materials produce different spectral responses. These responses form the basis of feature identification in remote sensing. Chapter 11. Spectral signatures. Every object has a unique pattern of energy interaction. This pattern is called a spectral signature. For example, water absorbs much of the incoming energy. Vegetation reflects strongly in the near-infrared region. Bare soil exhibits intermediate reflectance characteristics. Spectral signatures enable analysts to distinguish different land cover types. They serve as fingerprints for identifying Earth's features. Chapter 12. Remote sensing platforms. Remote sensing sensors are carried by various platforms. These include ground-based platforms, airborne platforms, satellite platforms, unmanned aerial vehicles. Each platform offers different advantages depending on the application. Chapter 13. Ground-based remote sensing. Ground-based systems operate close to the Earth's surface. Examples include spectroradiometers, terrestrial laser scanners, environmental monitoring instruments. These systems provide highly detailed measurements and often support calibration activities. Chapter 14. Airborne remote sensing. Airborne remote sensing utilizes aircraft equipped with sensors. Advantages include high spatial resolution, flexible acquisition schedules, detailed local coverage. Applications include engineering surveys, environmental assessments, disaster response, large-scale mapping. Chapter 15. Satellite remote sensing. Satellite remote sensing provides broad geographic coverage. Examples include Landsat Sentinel Spot. Worldview satellite imagery supports global environmental monitoring and resource management. Chapter 16. Active and passive remote sensing. Remote sensing systems are classified into two categories: passive systems, active systems. Passive systems rely on naturally available energy sources such as sunlight. Examples include optical satellite sensors. Active systems generate their own energy. Examples include radar, LiDAR. Active sensors can operate regardless of sunlight availability. Chapter 17. Radar remote sensing. Radar stands for radio detection and ranging. Radar systems transmit microwave energy toward the Earth's surface. The reflected energy is measured and analyzed. Radar supports flood mapping, forest monitoring, terrain analysis, ground deformation monitoring. Radar's ability to penetrate clouds makes it extremely valuable. Chapter 18. LiDAR technology. LiDAR stands for light detection and ranging. LiDAR systems emit laser pulses and measure the time required for their return. LiDAR generates highly accurate three-dimensional representations of the Earth's surface. Applications include topographic mapping, forestry, urban modeling, infrastructure planning, digital terrain model generation. Chapter 19. Image resolution. Image quality depends heavily on resolution. There are four primary types of resolution: spatial resolution, spectral resolution, temporal resolution, radiometric resolution. Each influences the quality and usefulness of remote sensing data. Chapter 20. Spatial resolution. Spatial resolution refers to the size of the smallest feature that can be detected. Higher spatial resolution provides greater detail. Examples include 30-meter Landsat imagery, 10-meter Sentinel imagery, sub-meter commercial imagery. The choice depends on project requirements. Chapter 21. Temporal resolution. Temporal resolution refers to how frequently a sensor revisits a location. Frequent observations are important for monitoring change over time. Applications include crop monitoring, disaster response, urban expansion studies, climate monitoring. Chapter 22. Image interpretation. Remote sensing data can be interpreted visually or digitally. Visual interpretation relies on color, shape, texture, pattern, size, association. Digital interpretation uses computational methods and image processing techniques. Chapter 23. Digital image processing. Modern remote sensing heavily depends on digital image processing. Common operations include image enhancement, classification, filtering, geometric correction, radiometric correction, change detection. Image processing transforms raw imagery into useful information. Before we continue, please remember to subscribe to this channel, like this video, share it, and drop a comment below. Your support helps us grow this academy. Chapter 24. Land cover and land use mapping. One of the most common remote sensing applications is land cover mapping. Examples include forests, agricultural land, urban areas, water bodies, wetlands. Land use information supports planning and resource management. Chapter 25. Remote sensing applications. Remote sensing supports numerous fields: agriculture, forestry, mining, urban planning, hydrology, disaster management, climate science, environmental monitoring, defense and security, infrastructure development. Its versatility makes it one of the most valuable technologies in geospatial science. Chapter 26. Remote sensing and GIS. Remote sensing and GIS are closely linked. Remote sensing provides data. GIS manages, analyzes, and visualizes that data. Together they form a powerful geospatial decision support system. Chapter 27. Emerging trends in remote sensing. The future of remote sensing is being driven by artificial intelligence, machine learning, cloud computing, CubeSats, drone mapping, real-time Earth observation, big data analytics, digital twins. These technologies are expanding the capabilities of Earth observation systems. Conclusion: remote sensing has transformed humanity's ability to observe and understand the Earth. By measuring reflected and emitted electromagnetic energy, remote sensing allows us to collect information without physical contact. From satellites orbiting hundreds of kilometers above Earth to drones flying over agricultural fields, remote sensing systems provide critical information for science, development, environmental management, and decision-making. Today, remote sensing forms one of the most important pillars of modern geospatial science. As sensor technologies continue to evolve, our ability to monitor the planet will become increasingly sophisticated, accurate, and timely. Thank you for joining this episode of Geospatial Science Explained. In our next lesson, we will explore electromagnetic radiation and the electromagnetic spectrum in greater depth, examining how energy interacts with Earth's surface and how remote sensing systems exploit these interactions to generate meaningful geospatial information.